This is question Q5a. What is the purpose of zero padding? Given xn, a sequence with 3 samples, so here with n equals to 0, the first sample, second sample, and third sample. Of course, once we are given that, we are assuming that the rest of the sequence is 0. We can, of course, take Fourier transform of this, but then you'll be using n equals to 3. Typically, we do not like to take Fourier transform of number of samples that are not power of 2. We like 2 to the power of 3, 2 to the power of 4, 2 to the power of 5, and so on. Because when we take a sequence with 2 to the power of n, where n is an integer, it will allow us to perform efficient Fourier transform. So to extend the sequence from 3 samples into, in this example, 8 samples, we are going to pad it with zeros. Basically, zeros contain no information. We're just saying that we are going to realize this extension of zeros of the sequence, and now we have 8 sample x of n, and we can take the Fourier transform or discrete time Fourier transform, and that allows for efficient Fourier transform. So this is one of the reasons why we want to increase the length of the data. When we increase n equals to 8, we are also increasing the frequency resolution for visualization. Remember that this is the horizontal axis for omega, and how we divide this 0 to 2 pi, each of these steps is actually 2 pi divided by n. Okay, so this is 1 times 2 pi divided by n. This is 2 times 2 pi divided by n. So the larger the n, the finer the spacing in between. You have to be very careful when we pad 0. Although we are plotting a smoother curve, there's actually no extra information given to us. Okay, so you have to read that very carefully. But basically, we are saying we can increase the frequency resolution for visualization, but there's no additional information because only zeros are added. The second reason why we increase or why we zero pad is to perform multiplication in the frequency domain, to perform convolution, and we want to overcome something called circular convolution. Okay, so how to overcome circular convolution? Well, when we convolve h and x in the time domain, and in the time domain, and when we are doing it in the frequency domain, we're actually multiplying the discrete time Fourier transform of x and discrete time Fourier transform of h. But when we're doing it using DFT, or actually FFT, the fast implementation, then x and h are actually pseudo periodic sequences. Yeah, because discrete Fourier transform DFT is nothing but DTFS in disguise. So to overcome that, we must zero pad it such that the length of the sequence x and h must be extended by its length minus 1. So for example, if length of x is, let's say, 3 and the length of h is 5, we must actually use 3 plus 5 minus 1 is equals to 7. And of course, we can again zero pad it and we increase it to 8. Up to us. But we have to do this. Okay, go and read about circular convolution here and how does zero padding overcome circular convolution. The diagram of this idea is this. X, for example, has length 3. H has length 5. Well, we're going to pad it. Okay, so we're going to pad it by what? M minus 1. Where's m? So m is 5 minus 1. So what is L is 3 plus, what was I doing? 3 plus 5 minus 1. Answer is 7. So we are going to have a 7 point. And to have a 7 point, we have to add 4 zeros here. And here, we have to add 2 zeros. So X is extended by 4 zeros, H is extended by 2 zeros to make them the same length, 7. So when we have 7 point, then XK is also 7 point, HK is also 7 point, and then now we can multiply, right? X has 7 numbers, H has 7 numbers, we can multiply both of them together. So then this YK is a 7-point DFT representation in the frequency domain. When we inverse, we will get a 7-point values in the time domain. Of course, we can add more, 8 points, to make it the 2 to the power 3. But this is the diagram to show what's happening when we are doing zero padding. We're taking Fourier transform of the zero padded sequence, and we are multiplying the X padded with the H padded in the frequency domain. Alright, now this is question 5b, and now we have a real example. In this example, H is 4 sequence, N equals to 4, X is 2. So how many do we need? We need 4 plus 2 minus 1. So we need a 5 sample sequence. Okay, so what do we do? Well, first I want to show you what convolving H and X look like. Convolving X and H will give you a 5 sample sequence. So this is Y1. 1, 2, 3, 4, 5. So N equals to 0 is here, N equals to 4 is here. So capital N equals to 5. So convolving a 4 sample sequence with a 2 sample sequence result in a 5 sample sequence. Now, so what do I do? Well, remember, we have to zero pad X. You can zero pad X and then take a Fourier transform, or you can just simply state that I'm going to take a Fourier transform given X with 5 samples. So if X is less than 5, then it will zero pad it by itself. Okay, so H is also same. I zero pad it. I say that make Fourier transform of H using 5 samples. So therefore now X and H are complex numbers with 5 elements, and this is 5 elements, so now I can do element-wise multiplication. So I get Y2, and then I inverse Fourier transform of Y2, I will get 5 element sequence of time, and then now I see this, and you'll see that it's the same. Okay, so the sequence Y1 and Y2 are the same, showing that how we are doing Fourier transform in the frequency domain to realize convolution. And of course, you'll be thinking, why are we doing this? Well, in the real cases, N here in the what do you call it, in the industry, N can be as big as 256, 512, even 1024, and so on. So imagine that Fourier transform is cheap, and then we are doing this, and then we are doing multiplication by element wise. It's really cheap. So even though we're doing inverse Fourier transform, it's still cheap. Well, if we have done it in convolution, it will be n squared operation. Here's n log n to realize convolution in the frequency domain. So that's the reason. So let's come back to this question again. This question basically is showing us how to realize DFT for convolution, and that little code is actually doing this. Okay, that's it. Thank you.